Okay, so this is strong acids, strong bases, weak acid, weak bases. Strong acids or bases are very product favored because they dissociate 100%. In order to calculate the hydronium ion or the hydroxide ion or you use stoichiometry. There are 7 strong acids that you have to memorize. First one is hydrochloric acid, HCl. The second one is hydrobromic acid, HBr. The third one is hydroiodic acid, HI. The next one is nitric acid, HNO3. The next one is sulfuric acid, H2SO4. The one after that is perchloric acid, which is HClO4. And then finally, chloric acid, which is HClO3. If it's not on this list of strong acids, then it is a weak acid. The strong bases are hydroxides, either the group 1A or 2A hydroxides. So for example, and I'm not going to list them all, there's about 8 of them. Anything in group 1A attached to a hydroxide, and calcium, strontium, barium in group 2A attached to a hydroxide. These are all the strongs that you have to know. Kindly notice also on your list of acids, 1, 2, 3, there are 3 binaries. These 3 are binary acids. And there are 4 oxy acids. In order to name the oxy acids, you have to know the ion acids. Weak acids and bases are very reactive favored. If they're not on the list of strongs, then they are weak acids and weak bases. With the weak acids, they do not dissociate. They have different dissociation capabilities, and the size of K determines the strength of the weak acid or weak base. And remember, the larger the K, the stronger the acid. In order to calculate the hydronium ion or the hydroxide in the case of bases, you need to do ice table math. Right, here's a little pictorial. Notice on the left, hydrochloric acid, which is one of the strong acids, and on the right is hydrofluoric acid, which is a weak acid, because it is not on the list of strongs. On the left, you can see that at equilibrium in the solution, there is only the hydrogen ion and the chloride ion. There is no HCl, the compound. On the right, at equilibrium, it's different. You have the hydrogen ion, the fluoride ion, and the compound in equilibrium. Also notice that for hydrofluoric acid, there's a lot of compound in the solution. All right, a relationship between Ka and Kb. So what I'm going to do here is I'm going to write out two reactions. Reaction number one is acid, so I'm going to give it a chemical name. There's its conjugate base. And then what I'm going to do is conjugate base. So I'm going to write what it does in water. And what it does is it acts like a base. And base is out protons. So you have here two reactions that are very much related. The first reaction is an acid, a weak acid. And the second one is technically a conjugate base. What I'm going to do is, for this one, I'm going to write the K. Now notice I leave water out. For the second one, since it's acting like a base, I'm going to write the Kb expression. All right, now what I'm going to do here is to show you that there is a distinct relationship between Ka of an acid and its conjugate bases Kb. So I'm going to multiply the Ka times Kb gives you, fill in my Ka, times it by the Kb. Now you'll notice some very similar ions floating around here. And we're going to do a little cancellation. Notice that this is in numerator and this is in denominator. It cancels and cancels. Notice that what you get over Ka times the Kb, the hydronium ion, hydroxide, which is of course Kw. And at 25 degrees Celsius, Kw has a numerical value of 1.0 times 10 to the negative 14. So the relationship between Ka and Kb is Ka times Kb is equal to Kw. Given one, you can find the other. For example, here are two weak acids. I'm going to go through some qualitative and quantitative analysis of two acids, two weak acids. I know they're weak acids because of two reasons. Number one, they're not on my list of strong acids. Reason number two, they both have K's, which is like really big are weak acids. The first one is called hypochlorous acid. It is an oxyacid made from the hypochlorite ion. Then the second one is chlorous acid. It is also made from an oxy anion. Now, which of the two is stronger? Compare the K's. Ka of the chlorous acid is larger than the Ka of the hypochlorous acid. It is a stronger acid. So this guy's stronger acid, this make sure we write that word. And this guy is the weaker acid. Now, keep in mind that opposites will create in water an opposite ion, strength-wise, let's say. So if it's a strong acids will give rise, or what I call give birth to, weak conjugates. Weak acids will give birth to strong conjugates. So of these two weak acids, what we're going to do is qualitatively theorize which one will have the weaker conjugate base, and then we'll do it mathematically. So we have the two acids staring us in the face, the two Kas. We've already determined that the second acid is the stronger of the two. So what we're going to qualitatively determine then is the fact that since the second acid is the stronger acid, then it is the weaker conjugate base. So a weaker conjugate base, and I'm going to abbreviate that CB. So since this is the weaker acid, I'm going to predict that this is the stronger conjugate base. Now we're going to do that mathematically. The Kb base, which is the OCl minus ion, will be Kw or Ka given, and that's 10 to the negative 7 of the conjugate base will be Kw, Ka, and then that's going to be equal to 8.3 times 10 to the negative 13. Notice this guy is the bigger number, so it is the stronger conjugate base. So not only did we theorize it, we mathematically computed it, got the same